Right. Good morning, everyone. Please let me know if you are able to see my screen. Okay, thanks. All right. So in the last class, we were discussing GAN and the kind of machinery that we built up was we wanted to go towards likelihood-free learning. Okay. So why we wanted to go towards likelihood-free learning is because when we took a model which has 99% noise and 1% samples coming, 1% sample coming from true distribution. And we saw that the maximum likelihood, the maximum likelihood, the sandwich that we get between the lower bound and the upper bound is just basically log of 4. All right. So essentially, it's a very narrow bound. And um, theoretically, it has been proven that only and only if P of data is equal to P of theta, that is, it exactly matches your true distribution matches the data distribution, that is true distribution matches your model distribution. And in that case, your sample quality will be, you will get the best sample quality and out of the framework. But we all know that in practice, and we can never make the model distribution to the true distribution. It is just a approximation, and when it is approximation, the model obviously your maximum likelihood is not a true reflection of your is not always a true reflection of your sample quality. Okay. And we also saw one other case where your sample quality were very good, but your maximum likelihood was bad. That was in case of overfitting. And hence we wanted to kind of move towards likelihood free learning. And when we moved towards likelihood free learning, we came up with this GAN framework, where you have a discriminator, which is nothing but a classifier. The classifier, so the classifier is essentially its main job is to distinguish between in the samples coming out of the true distribution, that is your training examples, and the samples coming out of your um, model distribution. In this case, the model is nothing but a generator, which takes some Gaussian noise and converts it into some samples. All right. So two divergent objectives here. The objective of the discriminator is to discriminate the real samples from the fake samples. And the objective of the generator is to make sure that, the discriminator is fooled and it is not able to distinguish between the two samples, that is the true samples and the fake samples. All right. Fake samples is just the samples coming out of the generator. So in that case, if it is not able to distinguish, in the case where it is not able to distinguish between the true samples and the generator samples, it essentially means that both the distribution are same because the samples are same. And, and, and that is how we train a um, GAN, right? So the way in which we went about it is that we saw that ultimately what we are doing, all the components remain the same. We are only going to play around with this particular component. Okay. And when we played around with this particular component, we saw that this particular thing, and that is, we have been using KL divergence here because maximizing the likelihood is equal to minimizing the KL divergence. But in case of GAN also, we saw that we landed up in some form of divergence, which was the Jensen-Shannon divergence, right? So just a quick recap. So choose P data P theta to be a two sample test statistic. Learn the statistic by training a classifier, that is discriminator, under ideal conditions equivalent to choosing. And this is equal to it is basically the same as minimizing the JSD or the Jensen-Shannon's divergence. Right? And the pros here are that lot of flexibility. I mean, loss only requires samples from P data, no likelihood needed. So that is basically what we are after. Lot of flexibility for neural network architecture as G theta defines just a valid sampling procedure. So you don't need an autoregressive model or something in like that. You can do a simple sampling procedure and obviously fast sample. And this is also why it is fast sample, because it is single forward pass. Unlike autoregressive models where you have to sequentially generate one sample at a time, because I mean the current one is dependent on the previous, and that thing is out of the window. All right. And the con is that it is very difficult to train in practice because, I mean, while theoretically it is fine that we are doing a min max game, but unlike MLE, where you will, after during the training, you will soon realize that your maximum likelihood is not going up anymore, or it is going a little bit down, then you can and stop to converge. Here it becomes very difficult to basically find out the optimum point and where you stop the training. All right. So the GAN training algorithm that we discussed last time is, what do? We sample we sample mini batch of M training points from your dataset D. So this is your training data. Then we sample mini batch of M noise vectors from PZ. This is the the input of the generator. All right. And then we update the discriminator parameter phi by stochastic gradient descent. So we take this objective function, uh, we basically fix theta, and we essentially do stochastic gradient descent and with respect to phi. And when we do stochastic gradient descent, so we use this objective function where we pass in all our x here, and we pass in our z here. Then the generator converts this into fake samples, and then we basically do gradient descent here, right? And then in the next step, what we do is we update the generator parameter, that is we fixed phi, and we update the generator parameter theta by stochastic gradient descent again. And now this time, obviously, we are doing it with respect to theta. Since we are doing it with respect to theta, this particular term is of no use, all right, because it is a constant. And we basically do the gradient descent again, right? We do the gradient descent here. So we repeat this gradient ascent, stochastic gradient ascent, and stochastic gradient descent multiple times. And we try to reach a optimum. But reaching the optimum is the most tricky part in GAN, and because of which GAN have basically, not only because of this reason, but few other reasons, GAN have fallen out of favor, and it has been replaced by diffusion models. Now, let's try to visualize this a little bit better. So this is your or objective function where you are trying to do a min max. All right. And in the bottom, what you are going to see is this is this is your generator, right? This is your generator. So generator takes Z and spits out basically fake samples. All right. Fake samples. Now, here the blue line that you are seeing, is the discriminator, the wiggly line. All right. And we have two distribution. One is the true data distribution, which is your red line, and one is the fake data distribution or your generator data distribution, which is your green line. And you see both of them are different. And if you see here, when you pass Z and pass it through the generator, when you sample Z and pass it through the generator, the data points are somewhere here, fake data points are somewhere here, and that is why the distribution is also like this. Okay. And when you start this algorithm, obviously you don't have a good generator, and that is why you see this particular zigzag line here. But now what is going to happen is, in the first iteration, you are going to update the discriminator. So the discriminator will try to say that anything on the left is a true sample, is coming from the true distribution, and anything on the right is coming from the fake distribution or the generator distribution. But something here in the middle, it is not so sure. Okay. And that's where the learning triggers in. Now what will happen is we update the generator. Once you update the generator, what the generator is going to do, generator is going to try to fool the discriminator. And the only way it can fool the discriminator is to make the samples as real as possible to the true or as close as possible to the true distribution. And that is where you see it has shifted to the left. And now the green Gaussian has shifted to the left, and or the data points have shifted to the left. And now you see that there is a certain amount of alignment between the blue curve, between the red curve and the green curve, or the green Gaussian or the red Gaussian. And now, basically, you see the generator, I mean, your generator is a little bit in a better, I mean, the discriminator is in a little bit better shape. Okay. And once you converge theoretically, ideally, what would happen? Both the distribution should be the same, and your discriminator is going to output 0.5 probability for all the data points. All right, it is completely confused. So this is, I mean, visually, this is what is going on. All right. So these are the kind of images that a GAN is capable of generating. So both these images are actually generated by GAN. They are not real images. And you can see here, that right from 2014 to I mean pre-corona sort of time, and that is the time when GAN was doing very well. And so you see that the quality of the generations have improved so much. All right. But the whole problem with GAN is uh, it's mostly related to training. All right. And a few other things. So one obviously is the unstable optimization. Because you are doing a min max game, the optimization is unstable because you are doing a gradient ascent and a gradient descent, and both are diverging. So it tends to oscillate a lot. All right. Then there is something called a mode collapse, which we'll discuss. And obviously evaluation of GAN is also not easy. Now, the question is that even though GAN has fallen out of favor, it does not mean that GAN is not going to return back. It is a very powerful machinery. And maybe in the near future, it will make a comeback. Okay. Now, this is where you see this graph here. You see that, there is a lot of oscillation on in when you are training the GAN. So the generator and the discriminator laws keeps oscillating during the GAN training. And that is the problem, because you then have a hard time I'm basically converging, unlike the MLE. Okay, this is the key problem there. And there is one more problem of GAN, which is essentially called the mode collapse. Okay, now what is mode collapse? Now, what will happen is, I'll just give you a small example, and then when we go through the slides, it will become clear. You have a distribution like this. Now, this is, as you can see, this is a multimodal Gaussian. Okay, this is a multimodal Gaussian. Now, what is going to happen is, your generator is trying to basically generate samples as close as possible to your true distribution. Now, what happens in practice is, samples can, this is also high probability area, this is also high probability area, this is also high probability area. Now, what GAN is going to do, and you will see it from these examples. You see this particular samples. These samples are almost similar. And why it is similar is, during the training, what happens is, GAN will first try to basically explore the Gaussian space. all right, or the distribution space. And now when it sees that, let's say samples, when it samples from here, it will soon see that, I mean, these samples are doing very well and it is able to fool the discriminator. And in the process, what happens is it stops exploring these areas. Sorry, what is it? It stops exploring these areas and it only tries to basically pull in samples or take samples from this particular mode of the multimodal Gaussian. And that is the reason why you see that similar samples are popping up, because its goal is to fool the discriminator. And it succeeds in fooling the discriminator by doing this. And the generator thinks that it has learned the distribution and it kind of the mode collapse essentially happens. All right. So in a nutshell, in a nutshell, this is what is happening. The generator distribution keeps oscillating between different modes. It will keep moving around here and then somehow hone in somewhere here. And then, I mean, and then it stops basically generating samples from other nodes because it has found a way to fool the discriminator. Okay. So mode collapse means that the generator fails to sample from all the modes of the true distribution, right? So instead, it learns to generate samples from a small subset, often just one of those nodes. Okay, this is what it is. Now, if the true distribution normally, and if you have understood these things by now, if the true distribution is a mixture of Gaussians, then obviously want to learn the entire mixture of Gaussians, right? And we want to sample from all of them. And we want to basically generate the data that reflects the diversity of the multimodal Gaussian, right? That's what we want to do. Now, in case of mode collapse, what happens is that the GAN, or rather the generator, it locks into one mode and keeps generating from that particular mode and ignores all the other modes. And it still manages to do very well by fooling the discriminator. And you can see that in real life, what will happen is your GAN has trained very well, but then it will never be able to, I mean, its samples will be of low diversity essentially. It will have unrealistic coverage and it will fail to generalize. So that is what is the problem with one of the key problems with GAN, right? So, all right. So if you want to learn about, I mean, how there are various tricks and tips to train GAN. And so there is a nice GitHub repository available. You can go through it if you have time. And this is one of the kind of paintings which was, I mean, um, fake sample, that is, which was generated by the GAN. And all right. And if you see here that GAN generated art auctioned at Christie's, it was expected price was $7,000 to $10,000 and it went to around 432K. All right. So this is a kind of good samples that GANs are generating. Okay. Now, before I move any forward, any questions from anyone? Okay. All right. So I hope I have opened your mics. Enabled your mics. Just check. All right. So now we come to, we have talked about Jensen-Shannon divergence. We have moved beyond KLN, I mean, and we want to move beyond KLN Jensen-Shannon divergence. All right. So what we would be doing now is essentially trying to generalize this entire notion of divergence. So we were in a very specific zone earlier where we talked about KL divergence, where we talked about Jensen-Shannon divergence. But this divergence is actually a big umbrella under which many types of divergence come. And every type of divergence can be used for as a performance measure for your optimization. Okay, and we'll see how we do. So what choice do we have for this divergence or the distance? So KL divergence, we had, we used in autoregressive models and flow models, and a scaled and shifted Janssen-Shannon divergence in the original GAN objective, right? Now, the question is that we'll talk about something called the F divergence. Okay, and F is nothing but a function. All right. So when we say KL divergence is a specific functional form of F divergence. When we say Jensen-Shannon divergence, it's a specific functional form of what you call F divergence. All right. So we want to generalize this particular thing. So given two densities P and Q, the F divergence is given by this. So D of F between P and Q is equal to expectation of F from expectation of X from Q and F of P of X by Q of X. That is this ratio, where F is any convex lower semi-continuous function with F of 1 is equal to 0. Okay. So the key thing to note here is that convex, it should be convex. All right. Lower semi-continuous, you just ignore it for the time being, and let's not make our life too complicated. And the other thing is that f of 1 is equal to 0. That means when p of x is equal to q of x, this ratio is equal to 1. And when this is equal to 1, this particular, the divergence should be equal to 0. So that's the constraint. Okay, we know what is a convex function, so I'm not going to go through it. Lower semi-continuous, I will skip for the time being. And let's talk about a little bit about uh, how we get this f of 1 is equal to 0. Okay, so your f divergence is given by this. Okay, and you have an expectation and you have a function. Okay, and you have a convex curve. So obviously we can bring in Jensen's inequality here, and we can bring the function outside and push in the expectation inside. When we push in the expectation inside, this expectation of x over q, we can simply write it as integral of qx, right? And then this qx and qx cancels out. We are left with integral of px, and we know that the sum of a distribution is equal to 1, and obviously f of 1 is equal to 0. All right. So now you see one thing. The first thing is that you're similar to what you saw in similar to what you saw in um, what do you call KL divergence and Jensen-Shannon divergence. We see that even F divergence, which is the umbrella divergence, um, it essentially has this nice property where your um, where it is non-negative, or that is always greater than 0. And when both of them are equal, it is equal to 0. And the form of this F divergence in case you want to replace it with KL is this U log U, right? How does it how it becomes like this? So you see here, I'll tell you how it becomes, but here these are all the divergences that are there, and these are the generator functions which are here. Okay, and this is our old friend KL divergence. Here you will have the Shannon divergence. So if you plug in the values here, you will get KL divergence, you will get Shannon divergence, but everything is ultimately represented by this particular thing, which is basically the F divergence. Okay. So the way in which this F divergence works, I mean, I'll just give you a simple example, is we said that U log of U is nothing but the KL. Okay. And why is U log of U I mean equal to KL? And so the way in which we can go about it is, all right. So let's plug in the formula. So now if you put in DKL, okay, if you put in DKL of P and Q, all right, P and Q, obviously. So we can simply write this. What is this U? This U is nothing but the ratio of P of X by Q of X, right? So we'll take the expectation of X over Q and we'll say P of X by Q of X into log of P of X by Q of X. This is the form. Now this expectation of this I can write as Q of X. And now if I simply put in the values here, P of X by Q of X log of P of X by Q of X, what will happen? These two will cancel out. And what is the functional form that remains? The functional form that remains is P of X log of P of X Q of X dx, all right? And this is nothing but your KL divergence, right? So actually, you can see that everything is coming from F divergence. Everything is coming from F divergence. It's just the functional form of the F divergence is changing. All right. So the whole goal of telling you about F divergence is because we wanted to come out of this specificity of Jensen-Shannon divergence, scale divergence. We want to make sure that we have an algorithm which works irrespective of the type of divergence that you essentially want to put in. Okay, so you can put in any type of divergence, KL, reverse KL, Jensen-Shannon, etc., and the algorithm is going to work. And that is the whole idea, that we have moved beyond the KL and Jensen-Shannon divergence to F divergence, which is basically, as you can see, it is essentially the umbrella over all type of divergence generalization. All right. Now we want to train using this F divergence. So we have found a generalized form and we want to train using this generalized form. Now, so what we have given P data and P theta. We could minimize either this d of P theta by P and P data, or d of P data into P theta as the learning objectives. Non-negative and 0 if P theta is equal to P data. Okay. However, it depends on the density ratio, which is unknown. Okay. Now, what is it trying to say? It is saying that you have this F divergence. F divergence is given by this particular formula, that is F of P theta. If it is the divergence between P theta and P data, it is going to be F of P theta by F of P data X. And obviously you have an expectation on the outside, and the expectation is over samples of P data. Now, if you want to calculate this, the first thing you notice here is that there are some problems here. First is you need to calculate the expectation, you need samples from P data. No problem with it. We have our training data. We have access to the samples. Can we have P theta? Yes, we have a model generator. We can have, we can calculate the P theta of X. But this particular term, p data of x, we do not calculate because we cannot calculate because we do not know the true distribution. We do not know the true distribution, right? We have samples from the distribution, but we do not know the true distribution. And if we take the reverse case, this is also the same, right? I mean, we can approximate the samples of p theta, but everywhere we don't have this. So ultimately, the whole point boils down to the fact that we cannot calculate this ratio of p theta by p data or p data by p theta, whatever we it is. All right. So now the question is that to use F divergence on a two sample test objective as it is written in this particular last line, for likelihood free learning, we need to be able to estimate the objective using only samples. So remember one thing, we went away from the likelihood zone. If we went away from the likelihood zone, we don't need this kind of things here, which is basically calculating the probability of a data point and for the generator or the true distribution. I mean, we don't know the true distribution. That is just, I mean, that is one fact that we have to recognize. But also along with that, we don't want to use this kind of expressions where we calculate the probability. Why we don't want? Because we want to work with samples. We want to go away from likelihood free. We want to do likelihood free training. Okay. So that is the main point. Now, one thing should be clear to you at this point of time is that build up or the machinery that we have built up now says that you have an optimization problem. You have an optimization problem, but you cannot solve this. But you cannot solve this. So you remember that you remember from your I mean previous semesters that whenever you come across this kind of problems where the primal form cannot be solved easily, then you need to basically explore the duality. Okay. And in this case, we are going to use something which is called the Fenchel conjugate. Okay. We are going to use something called the Fenchel conjugate. And I'll not go with the slides. I'll explain you the Fenchel conjugate and how we essentially do it. Probably that will become a little bit easy for you. Okay. So we said that f of u, the first thing that we said here, and let me change the color. Okay. The first thing that we said here is f of u is a convex function. Okay. All right. Now we know how a convex function looks like. Okay. Now imagine we are trying to approximate it. So ideally, when you have this convex function, how would you approach the optimization problem? The optimization problem, I mean, you can take the derivative and you can basically move down the curve and you come to a you come to a convergence point and your problem is done. Okay. But the whole problem in our case is that that ratio is that ratio cannot be calculated. So we'll have to take some other route. Okay. So now imagine that we are trying to approximate it from below using a linear function. Okay. So what I'm going to do is I'm going to approximate this using a approximate this from below. using a linear function TU. Okay. The idea is that your TU will always be less than equal to f of u for all u. Okay. Now the question is, okay, so all right. Now let's try to see what exactly is happening. So this is the convex function f of u, and the function in case of the GAN setup is difficult to solve because it involves the ratio of p of data by p of theta. Okay. Now, geometrically, essentially, this graph is a curved surface, and at every point we can draw a tangent. We can draw a tangent here. Sorry, this is bad. We can draw a tangent here. 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 Right? Now, each tangent line is basically lies below the function. Okay, and it touches exactly at one point. So now remember where this is going. This is going to, we are trying to do this, and let me, we can have a tangent here. We can have a tangent here. Just ignore the space. Okay. We can have a tangent here. 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 Everywhere we can have a tangent. Each tangent touches this curve at a particular point. Okay. And when you draw all these tangents, what happens is you will be able to approximate your convex function. Okay. So thus the function that is f of u is the upper envelope of all the supporting lines. Okay. Upper envelope of all the supporting lines. So this particular function, that is f of u, I can say is the supremum, okay, of supporting line at slope t. Okay, t is the slope of the tangent line, and there are lots of slopes which are different slopes which are available. What we are saying, this function f is the supremum of all the supporting lines at slope t. All right. Now the question that comes to my mind is, uh, how many of you know what is a supremum? Anyone?
Supremum is
No, sir.
max of min.
Max of mean. Exactly. So supremum is this. For those of you who don't know, supremum is this. So let's say we have a set of like this 1, 2, 3, 4, 5. Here the maximum and supremum are same. But let's say we have another set which is 1, 2, 3, 4, and then we have 4.9, we have 4.99, we have 4.9999, and it never reaches 5, but it's 4.99999. All right. So what will happen is your supremum in this case, here both the maximum and supremum were 5. Here the supremum is 5. Your maximum is actually 4.999999, and your supremum is actually 5. So supremum is like a maximum but more flexible. It is basically the smallest number that is bigger than or equal to everything in the set. That is supremum. Okay. And this particular function here this particular function here is saying that the f of u is the supremum of all the supporting lines. That is, this particular line here is the supremum of all the supporting tangents. Okay. Now, each supporting line there will have this particular form. Okay. So you have line of T u is equal to Tu minus f of star t. F of star is nothing but the conjugate function. Okay. Now, how do you geometrically think about it? So this is actually line of straight line. Okay. It is basically Tu minus f of star t. Okay. Now, how do you geometrically visualize it? T is essentially the slope of any of this tangent. Take any of this tangent. T is the slope of this particular tangent, and f of star t, which is the conjugate function, is essentially nothing but the vertical offset, essentially, that places the line just touching f. Okay, so it is the vertical offset that places the line just touching f. So you have a slope. Now let's take this particular tangent. Now you can have multiple lines here. 1, 2, 3. All of them have this slope. But we want the slope. We want the line which just touches the curve. How will you do it? This particular term, the vertical intercept f of star t, ensures that this line just touches the basically curve. So the conjugate essentially encodes the geometry of all the supporting hyperplanes. So all the supporting hyperplanes are defined by the conjugate. Okay. Now we have this particular form. This has nothing to do with machine learning. Okay. This is an optimization problem. Now we just transfer this to the machine learning scenario. Now, if we transfer this to the machine learning scenario, we want to replace this u, scalar u. We want to replace this scalar u by the density ratio p of x by q of x. And we want to approximate this line using a functional form, which is going to be t of x. And you understand that in f divergence, what was happening? So f divergence, what was happening? F divergence is written like this. Right? And we said that this is not possible to calculate. This was our fundamental problem. And here what we have done is we have replaced this. We said that u is this particular term, which we are not able to calculate. Now, what can we do? Now, remember this functional form of this particular line. Okay. Now, what we can do is we can substitute f of u. Okay. What we'll be doing here, we will basically plug in all the values plug in these particular values in the equation. Okay. Now this particular equation takes this particular form. Right? This takes this particular form. Now, when this takes this particular form, what happens? Tx plays the role of t. What was your T in the earlier in the actual optimization problem, in the Fenchel conjugate optimization problem, or the convex conjugate optimization problem? Your T was the slope of each of the lines that were tangent to your curve. All right. Now here T of x, we have changed it to a functional form, T of x, which will basically give the slope of T. And U of U is represented by this density ratio, which is P of x by Q of x. Now, what we can do is, in this kind of setting, we can always, this is an expectation and this is a supremum. Okay. We can always make it like this. We'll put in the supremum, we'll take the supremum outside. All right. And you will bring the expectation inside. And when you do it, what happens is this becomes P of x into P of x, Q of x. All right. And just I'm removing this bracket here. And this is going to be minus E of x from Q, F of star P star x. Right. Now, what happens here? Now, remember, one thing is that let's concentrate on this particular part first. This particular uh, part can be rewritten like this. This is expectation of x over q. All right. I can easily write it as q of x into t of x into p of x by q of x dx. This and this cancels. And now you can see that this is an expectation of x over p, because this particular integral and this, all right? And this is essentially t of x. So this simplifies now. All right. And finally, the equation becomes like this. This is the equation. All right. And you notice this particular equation now, there is no density ratio here. Okay. We have got rid of the density ratio. And if you convert this into the objective function, and I mean more, if you want to make the notations more understandable, the notations is going to be this. Your objective function is going to be this max over phi I'm just writing it down. This, and see what is happening. So you have your samples p data, you have your sample p data, okay, samples from p data. You have your discriminator, which is t of ex. And what you are going to do, you are going, and basically everything now falls in place. All right. So your original min max function has been converted into a more generalized form, on which is this, and which does not involve anything related to anything related to what you call the ratio of p theta by I p data, or p data by p theta. And now this is a simpler problem to solve. And the way in which we are going to solve it is again by using again by using in your what you call the F divergence algorithm, which will essentially involve the minimization and the maximization. Okay. Now the question is that if I tell you, if I just give you now, this is my curve. This is f of u, right? And we will have these lines which are here, similar to what we saw. All these lines are there, all right? The tangent. Your x-axis is essentially the generator distribution. Your y-axis is is your y-axis is essentially the F divergence. Sorry, this is P of Q. All right, this is the divergence. And this particular line, they take the form of this. Now, remember one thing, each x coordinate is not a number. It is an entire distribution. Okay. And the surface of the curve is fixed for your F and your P data. Okay. So these two things are essentially fixed for your F and your P data. Okay. Now, what you need to notice here is that, and I'll first let me get one more slide here. I'll come back to this page in a while. Now you need to remember is we have different spaces here. All right. We have different spaces here. Object lives in and role. You have your X. X lives in the data space. And these are individual samples. Okay. I'm just putting in one here. 2. You have your T of X. It lives in the function space. And its role is basically to determine the slopes hyperplanes. 3 is essentially your Q, which is nothing but your probability of generator. Okay, so this is your distribution space. And here, this is basically the generator position. And the last is essentially your F divergence. This is a scalar. And this is the height of the surface. Why I wrote down this is because this particular x-axis is basically the generator position. All right. And this particular y-axis is essentially the height, which represents the divergence. Okay. Now, what happens when you run this algorithm? When you run this algorithm, the first thing you do is you fix the generator. Okay. You fix the generator because it's ultimately coordinate. I mean, you are doing gradient ascent and descent alternatively. So the first thing that you do is essentially you fix the generator. when you fix the generator, let's say at any point, okay, what the role of the discriminator is to find a supporting hyperplane at any point. Suppose that this is essentially Q0. At this particular point, the role of the sorry, not hyperparameter, the role of the the what you call discriminator is to find this particular tangent, tangent at that particular point. All right. So what it is going to do, it is going to basically find the line that just touches the uh, convex curve at that particular point. Okay. And as you can see, because we are not able to work with this particular curve, what we are doing is we are doing a local linear approximation here. So geometrically, essentially, this is nothing but the first order Taylor approximation at that particular point of the surface at Q is equal to 0. All right. So now this is the first thing that that your discriminator did. All right. Now we come to the generator. So now the discriminator has done its job. All right. Now we come to the generator. Now we have to move the generator. Now what will happen is we fix the discriminator and take a small step downhill. This was the point. Let's say this was the point. We take a small step downhill. Okay. And when we take a small step downhill, this you can see that this reduces the divergence here. Okay, at the y-axis, and the height reduces. Now, at this particular point, again, at this particular, we try to move downhill. All right. And at this particular point again, remember, we don't know this particular curved surface. We are not moving downhill against the curved surface. We are moving downhill against the tangent. If we move a little bit down in the tangent, we kind of diverge from the curve. All right. And then again, the generator kicks in and draws another line, which will be like this. Okay. And this process repeats, this coordinated process repeats in the function space till we basically converge. All right. So your generator G theta tries to minimize the divergence estimate. Remember. All right. And your discriminator T phi tries to basically tighten the lower bound. Okay. So your G theta tries to minimize the divergence estimate. All right. And your G theta, your discriminator T phi tries to tighten the lower, bound. Okay. This is the entire, algorithm. Okay. Now, any questions?
Yes, sir.
Go ahead.
Sir, you said that we will find the solution in the duality domain, not in the primal
Hmm.
domain.
Hmm.
But in the duality domain, we have to, hold this contour condition just to make sure that the solution in the dual domain is the solution of the primal domain.
Hmm.
So how we make sure that, because I don't see any conditions for those things.
So the condition, see, the condition is the conjugate condition. All right. The condition is the conjugate condition, and we have put in that what you call the functional form of the line. So we are saying in that line is going to touch the curve. All right. So see, the question here is that you need to understand one thing. The primal form here is your equation on which you are basically trying to solve but cannot solve because the ratio is unsolvable. So what we are trying to do here is essentially we don't know the curve. We are trying to put the boundary against that particular curve and then trying to do a coordinated ascent and descent so that we get to the point. Okay. So that's what it is. If you want to go more into the literature, I have already uploaded a GAN literature. You can go through it. You will most of the things will get clear in terms of how this particular thing will work. Okay. Anyone else has any question? I think there was one more. I see a few people raising their hand.
Yes, I
Uh,
had a question related to this Suprema. That's it. But
hmm,
it was very simple question. Like, suppose if we have a set of numbers which are like in ascending order, the numbers of the value of pi.
hmm.
So if it's like till 11th series, if there is a, then what will be the Suprema? Like because pi cannot be approximated, right? It's irrational.
So it is going to be the next highest number, real number.
Okay.
Okay. All right. It is the same as
Sir,
elbow approach. It is the same as elbow approach. Yes. So
may
ult ultimately, if you see here, if I just if I go to this particular curve here, this is the variational divergence minimization. So ultimately, what we are doing here is we are trying to basically find a lower bound, which is going to lower bound and is likelihood free with respect to P and Q. So that's exactly what it is.
Sir, I have a question with respect to the last slide where you had explained intuitively. So,
Hmm.
the role of discriminator you had told is to find a tangent at some point, and
Hmm.
the role of discriminator is then to go along the slope, and if slope is diverging from the curve, and then come back again. So, but our main this thing is that the curve is not, we are not aware of that curve. So, how the discriminator comes to know that along the slope it had gone inside the curve or diverged from the curve boundary, and now it has to
No, no, no.
adjust it.
We know the curve. We know the curve, but we don't know how to navigate. We don't. We are not able to get signals from the curve.
Okay, sir. Because this curve represents px oblique qx. No?
Exactly. This represents this f of u, which is basically p of x by q of p of x by q of x. All right. What we are trying to say here is that it's not that we don't know the curve. What we are saying is that we don't know how to navigate the curve.
Okay, sir. Okay, sir. Thank you.
All right. Okay.
So what do you mean by the navigate the curve? You are saying by the tangent because we
When
cannot find the
what
tangent of the
what
curve.
what happens when you do gradient descent? You take the derivative at each of the point and move to the next point, right? That's what you do. You take the derivative of here and you get the signal whether which side has the steepest slope, and you basically go around this particular slope. Then here again you take another derivative and you move here, and so on and so forth. You do this and you come here. So when we say navigate, when I am saying navigate, I mean that I'm taking the derivative and trying to move here. But I cannot take the derivative of this because this is I because of that unknown distribution. So that's what I mean that navigating this particular curve.
Okay.
All right. We have talked about this variational divergence minimization. Okay. Now the question is that there is a problem here. Okay. So we have seen that we can generalize the algorithm to F divergence, but there is a fundamental problem in how F divergence is defined. F divergence is defined like this. Okay. And remember that the support for Q has to cover the support for P. What do we mean by that? Let's see an example. Let P of X is equal to 1 at X is equal to 0. That means all the probability, it's a very simple distribution. All the probability mass is at 1 when X is equal to 0. And outside X, everything is outside X. If X is not equal to 0, it is 0. Okay. And Q of X is, it has its probability mass at X is equal to theta, or probability mass of 1 is at X equal to theta, and probability what you call X is not equal to theta, it is 0. Now, if you want to plug in these values in the above equation of F divergence, what is going to happen? If you want to plug in the values of F divergence at the top, you are going to see that if theta is equal to 0, in that case, if theta is equal to 0, that means that both of them are equal to 1. And if both of them are equal to 1, we get the, let's say the KL, we're talking about KL, let's say the KL is 1. Okay. And however, if there are points in the, if X is not equal to, I mean, if theta is not equal to 0, then what will happen is this particular Q of X will be 0 and this P of X may be 1. Okay. In that particular case, we get an infinity. All right. And this is actually, I mean, even though this is a hypothetical, I mean, not hypothetical, but this is a very simple toy example. But this is a classic case of disjointed support between data distribution and the model distribution. And it happens especially in the early training when both the distributions are totally different. Okay. Both the distributions are totally different. So it may happen that you have one distribution like this and the other distribution like this. So there is the disjointed support here. Okay. Distributions are this. Now, what do we mean by support here? Support here means basically the set of points essentially with non-zero probability. Okay. And the very problem with not getting support is that we do not get signals for learning. How will we know which point is better than the other? All right. And this is the fundamental problem of this kind of matrices or this kind of distance matrices like your F divergence matrices. All right. Because F divergence matrices uses the ratio of P of X by Q of X. And if at any point Q of X is 0, then this whole thing does not work. All right. So what we want to do here, what we want to do here is essentially we want to use a distance measure which is a little bit smoother. Okay, where even though you may have disjointed support, but it will not fall flat on its face in those kind of scenarios. All right, and that brings us to the next topic of GAN, which is called the Wasserstein GAN. All right, or the W GAN. Okay, now this is basically the Wasserstein GAN, or the distance, or the earth mover distance. All right, the distance is called the earth mover distance or the Wasserstein distance, and when you apply it to a GAN, it is called the W GAN. Okay. Now, what do you exactly do in W GAN? Now, first just understand intuitionally, and then we'll see where we go from there. Okay. Now, on the left hand side, you have a distribution P. On the right hand side, you have a distribution Q. Now, W Wasserstein distance or earth mover distance says that how much how much movement we'll have to make in Q to basically or in P to make it equal to Q. Okay, so on the left hand side you have some mound of dirt which is representing the probability distribution. On the right hand side you have another mound of dirt or pile of dirt. Okay, and the Wasserstein distance tells us what is the minimum cost to turn the pile P into the pile Q. Okay, this is what it is trying to say. It is trying to say that what is the minimum cost to turn the pile P into the pile Q if cost is equal to dirt amount into the distance we move. So before we go into the formula and everything, just understand one particular thing is that if we have to move a lot of mass very far, or if the two distributions are totally different, then obviously then obviously we'll have to do a lot of work. Okay, and the distance will be very large. If we are to just tweak the pile of dirt a little bit, then essentially we are in a zone where we don't have to make much movement. And even before going into the formula, if you just leave everything else, if you just take this, you are now seeing that we are in a zone where we are now calculating the distances between the 2 points. All right. And distances between the 2 points will never be infinity, and we will get support for disjointed points. And that is what is essentially this earth mover distance. Okay. Now, this earth mover distance, this earth mover distance formula is like this. It says that cost is equal to, now remember, cost which we are trying to calculate is equal to dirt amount into distance covered. All right, dirt amount into distance covered. Now let's look into this formula a little bit. Okay. Now, okay. Now, the first component of the, obviously this is nothing but the Wasserstein distance. The first component of the formula is essentially infimum of rho belongs to pi p and q, and then you have an expectation of xy from rho, and then you have the you have basically x minus y. Okay, now let me go into each of these particular component of the expression and try to explain. Let me get a all right. So the first thing that we are going to have, what are the variables? If you are able to understand these components, then everything is will fall in place. So what are the first thing that we have? We have P of X. P of X is nothing but a probability distribution over many values of X. All right, we know that, right? So this is basically a probability distribution over many values of X. The second component that we have is Q of X. Q of X is a probability distribution over many values of y. Okay? And so the mass in P is spread across multiple locations. Now consider that the mass of P, the probability mass of P is spread across multiple locations. Okay. Now, what you need to remember, and it is just from an intuitional standpoint, the mass of P, let me write it in a proper manner. Mass of P is spread across multiple locations. And when I say multiple locations, at the back of your mind, just keep this as a warehouse. Just consider this as a warehouse. Okay. And what we want to do, is we want to move it. I mean, we want to move it to match the layout of Q. So we want to move it to match the layout of Q. And when I say Q now, just consider that these are stores. We have warehouses where from things are coming and you need to put it in some stores. Okay. Now the fixed component here is row XY. This is basically a plan to move a particular X to a particular Y. All right. So this is a plan to move a particular X to a particular Y. Okay. Now, each of these row X and Y says, how much mass do I move from point X in P to point Y in Q? All right. So this says how much mass do I move from point X in P to point Y in Q. Okay? This is what it is saying. Now, remember one thing now, which 6. Now, the other key thing to note is that all these rows X and Y combined together will form one row. Okay. So if I say all these rows, all of these X and Y, all of these X and Y combined together will be one row. And this row, the specific name of this is called the transport plan. Okay. So now imagine you have an entire table of row X, Y across all combinations of X and Y. So this will be one full transport plan. All right. So what it is saying is that you will have an entire table of values row XY across all combinations of X and Y is called the full transport plan row. So you have one transport plan for every one transport plan of how to move from X and Y. And then the entire table of row X and Y across all combinations of X and Y is one full transport plan or a candidate for moving P into Q. So this represents basically the joint distribution between X and Q. Joint distribution that is between X and Y. Now, after these 6 points, you have a 7th point, which says that now there would be multiple combinations on how the movement from X to Y can happen. All right. So all right. Now we can just think about it intentionally. We can split the mass in many ways, right? From X equal to 0, we can, from X equal to 0, let's say X is equal to 0, we can send all the mass, we can send to Y is equal to 1. Or we can send half of the mass to Y is equal to 1 and half the mass to Y is equal to 2. So these are actually different plans or different different plans, that is row. All right. So every point can be moved in multiple ways. So item coming out of the warehouse or item coming out of the warehouse can go directly to store A, or half of the items can go to store A and store B. And there are different ways in which it can go directly to B. So there are different plans, and hence we need the joint distribution. Okay. So now the space of all possible rows, the space of all possible rows. The space of all possible rows is represented by pi pq. This represents all the joint distributions of X and Y. Okay. Now the question comes is that so this pi p of q is essentially the set of all the valid transport plans, which is gamma. So this one, gamma, so not rho, gamma. All right. And that sends out exactly p of x to x and delivers exactly q of y to y. Okay. Now we are interested in a combination that results in the shortest distance. That is the combination that we are interested in. So amongst all the valid plans in pi, p, and q, we want one that minimizes the total cost. That minimizes the total cost. Okay. And now if we go back into the formula, let's see the formula once. Okay. You now have you now know X and Y are 2 points in a X is a point in the probability distribution P of X, Y is a point in the probability distribution of Q. All right. And then you have your row, which is nothing but a transport plan of how to move X to Q, X to Y. All right. And obviously, all these rows, all these not rows, sorry, all these gammas combine together to form on basically the entire table will form one full transport plan. And then obviously we would have multiple combinations on how we can move from X to Y. And that is the reason why the space of all possible gammas is represented by pi P, P of U, which is essentially the entire superset. All right. Now, let's go through this in a little bit detail, in a little bit more detail. So the first thing that you see here, one new term that you see here is infimum. Now, what is infimum? Infimum is of a set is the greatest value essentially that is less than or equal to all the elements of the set. Okay, that is, it is the highest value that does not go over anything in the set. So that is infimum. All right. And the question is that what are we trying to say? We are trying to say here in the Wasserstein distance is that d of P and Q, that is distance of P and Q, is equal to infimum of gamma, which belongs to this superset of all the transport planes. All right. And then you have an expectation of X and Y, which belongs to a particular transport plane. And then you have calculate the either the Manhattan distance or the Euclidean distance, whatever you want to do, L1 norm, L2 norm, whatever you want to do. But here you are doing a L1 norm, you can and go ahead with it. Now, what it says is that where pi of P and Q contains all the joint distributions of X and Y, where the marginal of X is P of X equal to the integral of gamma xy dy. It means it is a constraint. All right. It means that your probability mass, the amount that you are transporting from P, can never be greater than can never be from P to Q can never be greater than P. All right, because you cannot transport more mass than you have. And similarly, on the other side, the marginal of Y is Qy, which is essentially you are saying that you cannot bring in more mass than you can replace. Okay. So now your gamma y given x is a probabilistic earth moving plan that wraps P of x to Q of y. And now you see one particular nice thing happening is that in case of disjointed what you call support, this particular thing does not fall flat. Okay, so this is essentially your earth mover distance or your Wasserstein distance. Okay, now the question is that all right. Now, okay. So any questions on this particular part? Any questions on why earth mover distance is needed and why we preferred, I mean, why we wanted to get around F divergence? Anyone? Or any other questions on any of the concepts that we have covered till now? Because we have gone through a a lot of machinery here. I just want to make sure, take a pause, and I want to make sure that, I mean, if there is any concept that we need to discuss again, we can discuss.
Sir, can you repeat what does the warehouse contains?
Okay. So warehouse is nothing but, see, ultimately you have a probability distribution, right? Of let's say P of X. Now, what is a probability distribution? A probability distribution is nothing but a set of data points that fall in this particular distribution, right? So what we are saying is each of what we are saying is that essentially um, mass in P is spread across multiple locations. So just let me draw it once. Okay, so this is a probability distribution. Probability distribution has mass at every point, right? The mass here is much higher than what it is here. All right. Now, what it is trying to say is that the mass in P is spread across multiple locations. So here, 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 here. Each of them is considered as one warehouse. And we want to move this mass to match the layout of Q. So we'll have another distribution, which is a little bit different. And we want to move some mass from here so that we can make it similar to Q. And what the concept it is trying to say is that for moving any mass from here to here, obviously, let's say you have a warehouse and you have a store. Now, obviously, the mass from here can go to store one. The mass from here can go to 50% to store one and 50% to store two. The mass from here can go to store three, or the mass from here can go to 33% in each of these three stores. So you have various transport plans from going from the warehouse to the store. Okay, of how a mass in a mass in P can be moved to Q. Now all these gamma X and Y. So all these, sorry, all of these combined together will be one transport plan. All right, one transport plan. So this is basically um, it's just a plan to move from particular X to a particular Y. Now there are all of these combined, I mean, gamma X and Y combined together will form one transport plan. The entire table of values of gamma X and Y across all combinations of X and Y is one full transport plan. Okay, so remember one thing is you have two distributions. Now there are multiple levels in which you can think. The first is you can take any point, move it to any different point. Okay, or move it to any two different points, three different points, anywhere you like. Now that is for a particular point, but here you have many points. So you have to create a transport plan for each of these particular point. Now each of these, when you combine together each of these particular individual transport pathways or plan, you get one big table, which is basically called the full transport plan or the entire transport plan. Okay, but remember one thing, similar to when you do joint distributions, what you can have multiple combinations of X and Y, right? Here also this is only one transport plan, one way in which you can transport all your access to Y. Now you can have several ways, permutation combinations. And all of these together combine to form this rho P of Y, P of Q. All right. So this is basically the entire hierarchy. So at the bottom part, at the bottom, what you are trying to do is at the lowest level, what you are trying to do is you are trying to move an X to a Y. Now that is one network, that is one path in which you can move. All right. Now what you do is all your X's can move to different Y's, and you will get different paths from X2, from each of your X to a particular Y. That entire thing is called the full transport plan. And then if you go one level up, you can do all sort of permutation combinations in terms of how to move each X to Y. And that will be your pi P and Q, which is basically the overarching transport plan. So that is essentially what it is.
Are all the transport plans stored as a rows in the joint distribution table?
Yes,
Okay. Out of all the rows, Infimum tries to take the optimized transport plan.
exactly.
Uh, Thank you, sir.
Okay. Any other questions?
Sir, just for my understanding, sir, like we had started from previous models like auto-regressive, and from auto-regressive to we went to variational, and from variational to we have come to GAN. Now in GAN, we are studying all these strategies as we are studying the variations of calculating that distance, but the underlying strategy of GAN still remains. So, or we are studying these strategies because each distance measuring strategy is giving us a kind of advantage in computational
Okay.
resources or memory.
Okay. So the first thing that we realized when we were working with KL divergence is that minimizing the KL divergence is equal to the maximizing the likelihood. And then
Yes.
we built up the story, and we said that likelihood is not always a true measure of the sample quality. We can have very good
Yes.
likelihood, but poor sample quality, and vice versa. Right? And that is the reason why we wanted to get rid of likelihood. Now,
Yes.
ultimately, when we are, if we go here, if we ultimately, yeah, if we go here, ultimately, the thing that we can play around is only this, because
Yes.
you have your training data, which you obviously, I mean, and that you get, you cannot do anything else with the training data. You have your model family in the form of neural networks. There can be various architectures, everything you can play around with it. But ultimately, the performance measure that we have is basically what you call minimizing the distance between the p data and the p theta. And that particular distance can be minimized in various ways. The first way we saw is KL, and KL was kind of interchangeably used with MLE, and we came across those disadvantages. Now, what we wanted to do is because of this MLE problem, we wanted to get rid of MLE. We wanted to get rid of MLE, and we wanted to directly compare the samples. We want to take a sample from P. We want to take a sample from Q, P data, true distribution, and the model distribution, and we want to directly sample, what you call compare. Now, when we directly compared these two things, uh, somehow using the mathematical uh, derivations, when we did I mean, we created a discriminator, we created a generator, and then we essentially sampled from both of them, and then we trained the discriminator to basically get fooled by the generator, so that it is not able to, I mean, and it is not able to distinguish between the generator samples, that is the true distribution samples, and the fake samples, sorry, the fake samples and the training data samples. Now, the question here is that um, you in doing this, we never talked about any distances or anything. We never talked about any distances or anything. But then when we went to when we went through this particular when we went through this but we when we went through this particular objective function, so we found this objective function, which is essentially the min max function. And when we did some derivations on this particular objective function, we found this objective function is nothing but a form of distance, which is called the Jensen-Shannon distance. All right. So
Yes.
we have landed in an area where obviously this is a distance function, and ultimately we need some form of distance function. But in this whole exercise, uh, we this was basically a very specific form of distance that we derived. All right, this is a very specific form of distance we derived. What we wanted to do is we wanted to generalize it to maybe something which is more flexible. Okay, and the
Yes.
way in which we did it is essentially this, basically the F divergence. All right. So because ultimately F divergence is the mother of all divergences, you take any of your F divergence, you plug in any of the form here, and you get one or the other type of divergence. And each of these divergence is a particular measure of the distance between your true distribution and the model distribution. Now, whether one is superior over the other is a different aspect that for which you have to study some literature. But I'm now giving the flexibility that I can use any of these, plug in any of these values of of a particular form of F divergence, and I get this particular thing. Okay. In this whole exercise, when we were trying to do it, we saw that we were again kind of getting into the area of likelihood, where we wanted to calculate the probability of X given by the model and the probability of X given by the data distribution, which is unknown. Okay. And two problems, fundamental problems here. P of data is always unknown, and we also don't want to do this particular thing. Okay, two things. First is, obviously it is unknown, we cannot work with it, but we also don't want to work with it because then it gives a flavor of MLE. We want to work only with samples. And then we went into that Fenchel conjugate zone, where we said that if we do, if we cannot solve the primal problem, and we use a Fenchel conjugate to kind of solve this particular problem, we get a form, which is essentially independent of this ratio. Okay, we get a form which is independent of this particular ratio. And now I can simply take the samples from the generator. I can take the samples from my training data. I can basically work with it to basically get the variational divergence minimization or a lower bound on and the lower bound is likelihood free with respect to P and Q. But then, and what we realized is, in when we go to train this kind of F divergence models, there is a fundamental problem in this particular model. The fundamental problem is when you start your training, and let's say this is your P data, there is every possibility that your P theta can be different from your highly different from your P data. And the objective of the training is to get signals of how to basically move your P data towards your P theta towards your P data. But because this is disjointed, we never get the opportunity. I mean, because it is disjointed, I mean, we are not able to, we are not able to, the model is not able to get any signals, and we are not able to train properly. And that is the reason why what we want to do, what we did was we went towards the Wasserstein distance, because of the fact that that is a more, it does not have any ratio or anything. It is more of a kind of something minus something. Okay, it's a distance kind of thing, proper, I mean, distance kind of thing, and it smooths out basically the disjointed thing. In the next class, what we are going to see is essentially how we can optimize this Wasserstein GAN, and to basically get this entire thing. Now, the whole problem here, the whole problem of this GAN is essentially related to training. Now, because we are working with samples, and because we have a min-max problem going on everywhere, because we have a discriminator whose objective is diametrically opposite than what it is of the generator. All right. The problem is that we are not able to converge properly. We don't know how to converge. I mean, there is no natural way of convergence. Yes, you can use different tricks to converge, but there are no natural way of convergence, something which was principled in MLE. Okay, and that is where GAN kind of loosed out the space, and some other models like the diffusion models and all those came into the picture. Any other questions? Okay, so then let's close the session for today. I mean, there was a lot of things that we covered. We'll finish up GAN next week, and probably we don't need the entire session for GAN. We'll see, and then we'll start with energy-based models. Okay. Thank you.
Thank you, sir.